right, you guys, this is your video for 3.2 part B, and it's about graphing linear functions. So just a reminder, a linear function has two variables. It could look something like y equals 3x minus 4, and when you have two variables in an equation, the answer is an ordered pair, x and y, that makes it true. So instead of solving for one variable, we solve for a set of two variables, and that represents where the solution can be true. So when we do this, sometimes there are distinct points and other times they're connected. And this is where we get into discrete and continuous domains. So let's just make a couple notes here. Domains are the x values on a graph. And they're also the independent variable. So in biology, right, we've heard of independent variables. And so that's what your domain is. And so when we look at these, the discrete domain only can be certain numbers. So these are distinct points. And then nothing in between. So they're not connected. And then when you have continuous data, you can see we drew a line, right? It consists of all the numbers on the number line. So this is connected and everything in between. Okay. So you might be thinking, like, what does that even look like? So let's move down the page a little bit and talk about real life context of what this could look like. So I want you to maybe think in your head of things that are discrete situations. So things that are not continuous, you're going to have like one of them and then another, but they don't kind of connect. Okay, I'll give us one to maybe get started. What if I said skateboards? I can have one skateboard, 2, 3, but I'm not going to have 1.2537 skateboards, right? It's not going to be continuous. I have 1 or 2 or 3 or 4 or so on. So some other things that are discrete could be the number of people, the number of songs on my playlist. And again, there's so many examples. I could do number of carrots. Okay, anything that has basically a whole quantity that's not going to have parts. So then the other example is continuous, like things that go on forever. And so when we talk about maybe people's weight, or really the weight of anything, right? If I weigh apples, okay, I can have continuous weight like 3.12 pounds, 3.13 pounds. Time is always continuous, right? No matter what, time is moving. Someone's age, like right now, I'm younger than I am right now, right? Age, it's time. Someone's height can be continuous if you're measuring something. So I'll just maybe put measurements depending on what they are. You could do length of songs. So this would be different. If you're comparing the number of songs versus the length of songs, right? Songs can be continuous. They can go on for different amounts of time. So hopefully that just gives you some like examples that help make this a little clearer. So we're going to apply it to some tables. If I look at this first one, it says the X value is the number of stories and the Y value is the height of the building. Remember, we do this for the X values. This is really important. So the X value is the number of stories in a building. Is that discrete or continuous? So I would say that this is discrete because I don't go up to the 2.5th floor of the hotel, right? We just go up to the first, the second, the third. So that is discrete, and it would help if I spelled it right. So let me fix that. Boom. Okay. Looking at the next one, again, we're looking at the X value. It's the time, and we actually gave this as an example. If you're talking about time, time is always continuous. All right, years, the number of years and the height of a tree. Can years be continuous? Can you be 1.5 years old? Or can you be 1 3/4 years old? Yes, it's along the same lines as time, so that is also continuous. And then the last one, we're looking at the number of relay teams. I don't have half of a team, otherwise I can't really compete, so this would be discrete. I'm going to have no team, 1 team, 2 teams, so on. Okay, flip your notes over, and this is the part that maybe gets a little bit more complicated, but it shouldn't be too bad. So we have a linear function, m equals 50 minus 9d, and it represents the amount of money in dollars of money after you buy D DVDs. This question's a little outdated. I don't think many of us buy DVDs anymore. We probably all have like streaming services, Hulu, HBO, but we'll do it anyway. So M is money, 9D is the DVDs. Now we have to think about what is the domain of the function. The domain is the independent variable. Okay, remember this. And the independent variable is the number of DVDs I buy. So that's going to be my X value. Okay, that goes along the X axis. So I'm going to say number of DVDs. Okay, and then the Y value is going to be the money spent. So I'm going to go ahead and put money spent on the y-axis. Okay, so when it says to find the domain, I'm just going to go ahead and try to graph this and see what it says. So if I plug in 0 DVDs, and actually I'm going to go ahead and let's label our graph. So 0, 1, 2, 3, 4, 5. Okay, let's go up to 6 DVDs. And then let's just think about this equation really quick. If I look at the amount of money, how much do I start with? I start with $50. So this is my starting amount. And I pay $9 per DVD. And I'm subtracting $9 per DVD. So I'm going to go ahead and just count by fives. So 5, 10, 15, 20, 25, 30, 40, 45, 50, up to $60. Okay, so starting here, I need to figure out how to graph this. Well, what happens if I buy 0 DVDs? Okay, so I'm going to go ahead and write these as ordered pairs. 0 DVDs, how much money do I have left? So if I look at my equation and I plug in 0 for 9D, I would have $50 left. Like if I buy 0 DVDs, I still have $50. What happens if I buy 1 DVD? If I buy 1 DVD, right, it's $9, so 50 minus 9 is $41 left. So I'm going to go 1 DVD, I have $41 left. If I buy 2 DVDs, that would cost me $18, so 50 minus 18 is 32. So I would have $32 left. If I bought 3 DVDs, and I'm just going to continue this pattern, right? So 3 times 9 is 27. 50 minus 27 is $23. So 3 DVDs, I would have $23. 4 DVDs, 4 times 9 is 36. 50 minus 36 is $14. Okay, and then if I bought 5 DVDs, I would have $5 left. And I can't buy 6 DVDs, I would run out of money. And I should not connect this line because it is discrete. And it's discrete because I cannot purchase or I cannot buy parts of a DVD, right? You're not going to go into the store and be like, I would like half of the Avatar movie or whatever. Okay, and then we already graphed it, so that looks pretty good. All right, let's go ahead and try the next one. So when I look at this next one, it says a 20-gallon bathtub is draining at a rate of 2.5 gallons per minute. And we need to write an equation. Okay, so similar to the one up above, the number of gallons is equal to, how much do we start with, right? We start with 20 gallons. And I take away 2.5 every minute. So think about what is independent here. So find the domain. What is the independent variable? The number of minutes. So the number of minutes depends or will influence how many gallons are left. So we're going to go ahead and put minutes on the x-axis. My hint to you is that time is always independent. Okay, so if you're ever struggling, if it ever has to do with time, it's always independent. Okay, and then the number of gallons. Okay, so let's go ahead and just do some math off to the side. So if I have 0 minutes, I have 20 gallons. If I do 1 minute, and actually let's just jump a few, like that way it will go a little faster. If I drain the bathtub for 2 minutes, how many gallons will I have left? So if I drain the bathtub for 2 minutes, how much would I have left? And if it goes down 2.5 gallons per minute, it would go down 5, so that would be 15 gallons left. If I drain it for 4 minutes, I would have 10 gallons left. And again, you could just plug it into your equation right there for M. 6 minutes, I would have 5 gallons left. And 8 minutes, I would have no gallons left. So I'm going to go ahead. I know I have to go up to 8 minutes and 20 gallons. Like those are my maximum amounts. So I'm going to make my scale. And I'm just going to count by twos. 2, 4, 6, 8, 10, 12, 14, 16, 20. Okay, so counted by twos there. And then I'm going to just count by ones. 1, 2, 3, 4, 5 minutes, 6, 7, 8, 9, 10. Okay, so let's go ahead and graph this. Again, if I drain the bathtub for 0 minutes, I start with 20 gallons. So I put my dot at 20. After 2 minutes, I would have 15 gallons. So 14, 15 right there. After 4 minutes, I would have 10 gallons. After 6 minutes, I would have 5. And 8, I would have 0. Now, I want you to think about this. Time is what? Is it discrete or continuous? Continuous. Okay, and we know this because you can have partial minutes. Okay, that's our unit, right? You could drain it for 1.25 minutes or whatever that is. So because it's continuous, you have to come in here and connect the dots because it can really be anywhere along that line. Okay, the last few problems are asking us to just fit a real life example to the picture. So the first one is discrete. That's really important to recognize, is that I need a discrete representation of the graph. And I'll do something that some of you are familiar with. Let's say that the x-axis is the number of tech decks bought and the amount of money spent. So if we look at this, if I buy 0 tech decks, I spend $0. If I buy 1 tech deck, it's $10, 2, 20, 3, 30, right? So it would tell me each tech deck costs $10. Okay, looking at this last example, okay, we would do continuous. And I would just make this time. I love making my x value time, and then my y value I would make something. So maybe this is the time versus the distance a bird traveled. Okay, so again, it could be anything you want as long as it makes numerical sense, and you should be good. Anyway, try some homework. Let me know if you have questions, and I will see you later.